All right. So just some more miscellaneous things that you can actually read. Virus is a virus which actually came back into increasing frequency recently, which I find to be a throwback because most malware nowadays is botnets, and it's just simple Trojans. They're not actually infecting by way of infecting PE files and stuff like that. And so virus is polymorphic in that the code of the virus body and stuff like that is changing around. It's an appending file infector. So like our virus, it attacks itself on the end. And then it's an entry point obscuring virus in that it's trying to hide where exactly its real code starts. And then there's the comment on the bottom, which you can read. And this one's sort of interesting because whereas ours, so back here, we said there's a variety of different ways that, the virus can get its code to run, right? It can start from the headers, attach itself, and, well, the two basic ways that we're talking about here is A, it just modifies the actual PE headers to point directly to itself, or B, it lets the PE headers stay exactly where they were, but then it takes the very first instruction in that location and it jumps to the virus code. This XPadge or whatever it was, this virus, which is the second slide there, it takes and it goes some random location into the binary, and it just picks a random location and it says, I'm going to put a jump there, just wherever. And so basically it disassembles that code, figures out which code would have been there, copies those instructions to its own thing, puts in a jump to itself there. And so the point from that little write-up from Semantic for the second one is that, the little summary says that, summary says most of them are very just simple in terms of what they actually modify, but this one will actually inject itself just at some random location, making fairly complex modifications. So point is now you can go back out and read these virus articles and understand a little bit more about what they're talking about when they're talking about attaching to the end of files, changing headers, etc. So you can see more about PE infection at these links, T-elf infection there, Mako infection there. The point of adding the Mako stuff is to say, as always, that there's no technical reason why Macs can't be vulnerable to all the same malware as other platforms. It's just they're not because people aren't trying. All right, so now we're going to talk about Packers. This is kind of this is mostly just to give you the briefest of introductions in order to let you have been exposed to it for any future reverse engineering class, because they're probably going to go in Packers. The reverse engineering class, or more probably the malware class. So they'll probably talk about Packers a lot. So the point of Packers originally was just to take a file and compress it down, but still have the executable run the same way that it always would. So you could take your hello world, compress it down, and when you double click on it, it still is hello world. It just decompresses itself on the fly. But nowadays, most of the Packers you're going to encounter are things where they're specifically trying to hide things from analysis. So, well, I'll just skip up here. So conceptually, whereas the virus thing had to do with attacking on code and changing it so that that code runs, what Packers do is we have some PE file, for instance. We've got, the .text section, .data section, .bss. That's not on disk. That slide is wrong. This takes up some amount of space on disk, right? And you want to decrease your size on disk. You want to fit it on a floppy disk or whatever. What the Packer does is it takes this data, compresses this down into, just some compressed data, and optionally it encrypts it, depending on if you ask for encryption or not. And then what it does is it takes and it adds in some unpacking code, which is what will actually be run when this file is run. So now we have a new file that has a big blob of compressed data, optionally encrypted. And then there's now some piece of code here, which when this executable is run, the only point of this code is to decompress that back to that. So that's it on disk, and I really do want to get rid of that. It says. right? So at runtime, right, so at load time, so load time versus runtime. So here I'm talking load time, and I'm just saying immediately when this compressed packed executable is loaded into memory, these file headers are changed such that this thing still gets located into a memory space which is sufficient to actually decompress the original executable. So if this was the original executable and it had, some space necessary for .text, .data, etc., when this packed executable is run, it still needs to allocate the same amount of virtual address space, actually probably slightly bigger amount of virtual address space that the original executable had. So it's saving file space, but it's not saving memory space or anything like that. And so then once you start actually running the unpacking code, the whole point of the unpacking code is it takes this compressed encrypted blob and it decompresses it into memory so that, there we go, magically in memory, you get your .text, .data, BSS, etc. And then finally, when the unpacking code has successfully decompressed all of the original code into memory, and it just goes and jumps to the original entry point of whatever the original entry point would have been if this code would have executed unpacked. So we're going to be going over UPX, which is one of the most common packers. And actually, the funny thing here is, despite being a very simple packer and being well understood by malware analysts, UPX is still one of the larger, one of the most common packers seen on malware. Basically, just due to laziness, ignorance, or they just don't care. If they have some malware, they'll just throw it through UPX. It'll compress it down. It'll hide what they want hidden, etc. So again, going back to this notion, what they're really worried about when they're choosing to use a packer is they're saying, if you could see my original malware, you could go in there to the imports table and say, oh, this malware is importing, connect socket or open socket, whatever this malware is opening the registry, etc. And so they want to hide those strings and they want to hide their code. And so by packing it down like this, when the malware analyst is given the thing, they don't know what functions it does. They can't do any sort of static analysis on this by itself. They need to actually figure out how to unpack that back out to the original code. We're going to be looking at UPX, which is basically a very simple thing, very, very cross-platform. You can use it on Windows, Linux, Mac, etc. And the nice thing about UPX, as opposed to a malicious packer, is that UPX has a command line switch that you can give it to pack a file, and then a command line switch you can give it to unpack a file. So if it's literally just a UPX packed file and the attacker has done no further modifications, you can just go grab UPX and unpack the file as is. But typically what they're going to do is they'll maybe throw it through UPX, and then they'll break some little signature saying this is UPX, and then the UPX unpacker thing won't recognize the file and therefore won't just unpack it automatically. So what reverse engineers typically do is they'll just put together little tools to automatically extract different packer formats. But that's a thing for the RE class. All right, so the main thing I want to show here is sort of this transition right here. So if I take something like Hello World and I run it through UPX, there's going to be some fairly big and obvious changes to its P headers. So in order to do that, I think I'm going to have you guys do this as well. Problem is I forgot to tell them to put UPX onto the thing. So got to go get UPX at upx.sf.net. So upx.sf.net, SF for SourceForge. So if you go there, then you'll see the download UPX link. Click the download UPX link, grab the zip file that is UPX. And just save that off to your desktop. So eventually you should have the saved file on your desktop. Open up that zip file and just drag the folder out to your desktop again. And so ultimately you should have this folder. Corey, in answer to your question, what am I using to make sure I don't reinfect the same virus file twice? There was a reserved field in the DOS header, which I set to hex pool. This right here, Corey, was the check where I say, if this thing is already set to hex pool, don't infect it again. Alright, so you should have UPX on your desktop now. You should have this folder. UPX is going to be a command line executable. So open up a command file. And I think we're going to want you to go to your desktop and that code folder and Life of Binaries. Life of Binaries, debug, right? That's where that hello world.exe was. So desktop code, Life of Binaries, debug. What I'm going to do now is, if I like just drag this upx.exe into this folder, or into my command window, it'll pull out the full path and throw it into the command window. If I just hit return on it, it'll tell me all of the command line options. So specifically, I'm going to use this -o option to output hello world to a new file called hello world packed. So I'm just going to, again, drag UPX in there and do -o space hello packed.exe space hello world.exe. And then press return. So again, all you have to do is drop the UPX in there and do UPX-O hello packed.exe space hello world.exe. And what you should see now in your, what you should see now in your directory is hello packed.exe. So the first thing that we can see is hello world took up 28K, and hello packed took up 9K, about 10K. So obviously the packer compressed it, but the question is, did the packer actually still allow it to execute as normal? So if I execute hello world, or hello packed rather, I just do hello packed.exe, press return, it'll still print out hello world, because the whole point of the packer is to make sure that the program can run and do the same thing it always would have done, but it just wants to compress it on disk. So now we're going to open hello packed with PEView, and we're going to open hello world with PEView, and we want to see, what the difference is between those two files. So I'm going to open hello world. And I'm going to open hello packed. Okay, Mike, that's fine. So you should see in PEView you have a hello world and hello packed open. And now you can just browse through and look at the section headers, for instance, and see the differences that you're going to see in the section headers. I mean, obviously you can see that one of them has completely different names. It's called UPX0 and UPX1 rather than .text, .data, and all that. Right? So there's one pretty obvious and big change to the P headers. Right. So like if I clicked on this image section header UPX0 in the packed one, it's saying that, okay, this section wants to be loaded at RVA hex 1000, and it wants a total virtual size of 1A000, but size of raw data is actually 0. So it's telling the OS loader, I want this much virtual memory, But you don't even have to bother with like grabbing anything from disk because I just want this much virtual memory. And, you know, UPX is going to do whatever it wants to do with that. So what we can infer from this is that this UPX0 section, the whole point of it is just to make sure that this executable has enough space to eventually map the decompressed version in, right? So if we go back to hello world and we try to see like what its size of image is, I'm guessing its size of image is on the order of 1A000. So we go to hello world, go to the optional header, and we look at the size of image. Yep, so close. It's 1B000. So it's not covering the entire space that the original would have. It's covering the entire space minus hex 1000. So looking at the next section header in the packed version, we can see that this one says, okay, I'm going to start at 1B000, and I have a virtual size of hex 2000. So between the two of them, so, okay, Mike, over to the board. So basically, I'm not going to break it down by sections for the hello world, but hello world asked for size of image equal to x1a000, and you know this will be broken up amongst some number of sections, but we don't care. We know that the total is that big. Hello packed, on the other hand, asks for, you know, well, I can look at the total size. I assume it's going to be 1C00. But if I look at the optional header and then the size of image, okay, it's asking for 1E000. Hello packed is saying, I want this much size, which is 1E000. So the packed version has to have at least as much size as the original version. And typically, it's going to have a little bit more virtual memory because it's going to need to have its own code in there to decompress the original code. Right? So if it didn't have greater than or equal to the, well, if it didn't have greater than the original virtual memory, then it would have its own code trying to decompress here, but it would, you know, decompress over itself. Yes?
Is this supposed to be 1A or is that 1B?
Sorry. Was it 1B? Is it 1B? Okay. So then, 1B. Thank you. Right. So this is 1B. And the point is, over here, the UPX0 asked for about x1a000. And this was the UPX0 section. That's right on the video. UPX0 section asks for hex 1A. UPX0 section, or 1 section, asks for hex 2000. 1 section asks for hex 2000. You can see that doesn't add up to 1E. So I'm still trying to figure out where the missing virtual size is coming from.
We got a header too. What about the B header?
What the resources, what about? Oh, yeah. I wasn't even seeing the resources. But yes. Resources is 1,000. Right. So 1A, B, C, D, but then the end of it is 1E, right? So it starts at, right, by the end of it, it's 1E, right? So this total size is 1A. No, that's not true. The total size here is 1A, so the end of it is 1A.
So we're still missing hex 1000. But you got to remove the headers. Again.
Well, the question is that... yeah, it is that, and it's more because of the fact that it's more like this. the UPX0 actually, so yes, it is kind of that you need room for the P headers, but it's more like this UPX0. It says my RVA, my virtual address, my start virtual address is actually hex 1000 into this. So that right there, this size starting at RVA hex 1000 is 1A, etc. So there's this this initial hex 1000 right there, which is before UPX0. So UPX0 starts hex 1000 in, goes for 1A. UPX1 starts, 1A in, or was it 1B in, right? UPX1 starts 1B in, because it's 1000 plus 1A, starts 1B in, and it goes for X2000. So we found all the virtual memory space. Good for us. All right. And yes, and there was that resource section. So that's how the UPX version of it looks in memory. It's greater than the size of the thing of the original was in memory, but it's smaller on disk.
Where's the compressed data?
Right. So where's the compressed data? It would be in this UPX1 section, I believe, because this UPX0 is saying size of raw data is 0. The UPX1 says size of raw data is 1E. So this is all just, virtual memory space. But for the UPX1 section, it's saying the virtual size is hex 2000. The size of raw data is 1E. So in reality, right here, there's going to be X1E00 worth of raw data out of the file into memory. In reality, it goes for hex 2000 amount of space. But only hex 1E of that was mapped from file into memory. And so this is where the compressed data is, and this is actually where the decompression code is as well. So see if there's a way I can prove that. Well,
the address of the entry point, is it 1CAF0?
1C
AF0.
Interesting.
So that gives room for 1AF0 data.
Sorry, hold on a second. I'm losing my train of thought. 1CAF0. That's going to be ends at 1B, so this is the confusing part. So this ends at 1B and then 1C. So it's still within here, right? It's at the very end of here. So this, so in terms of absolute, so this is just a size here, right? This is size of 1E, size of 1A. But this is like X1000. And then right here, this is X. I'm going to get rid of this. This is 1B000. And this right here is X1D000. Right there, right? Because we started at RVA 1000 and we go for 1A. And that means the very last address of UPX0 is 1B. Then we start at 1B00 and we go for hex 2000. So that means the last version is D. So when you say the address of the entry point is at 1CAF0, was it? I think?
AF0.
AF0, right? When you say the address of entry point is at 1CAF0, it is still within this UPX1 section. So there's going to be some compressed data up here, and then there's going to be the actual decompression code somewhere within this range. And so we can, roughly speaking, try to start seeing that. So given a binary where the only thing we know is, well, we can check, we can say, okay, it doesn't look like it has any TLS callbacks, so we'll go ahead and we'll set a breakpoint on this packed version, and we're going to load it up in the debugger, set a breakpoint at 1CAF0, offset from the base address, and then we'll start seeing the unpacking code. So open up WinDebug, and then open up hellopacked.exe. WinDebug, file open executable.
I'm skeptical.
You're skeptical?
But the assertion of the packet is not UPX1.
Yep.
Just because it starts at 1B.
Well, hold on. I was going to do a calculation to try to kind of back that up. So let's see what so let's say that it starts at 1B0 and it goes to 1CAF0, right? That implies that there is only 1AF0 worth of packed data right there, right? And so you may be correct. It may just go out and actually read the thing from disk at some other location. But let's see. So what is 1C, or what is 1AF0 in decimal? 1AF0 in hex is decimal 6896 worth of data. So we've got about 6K worth of data ostensibly there. But we know that the overall file is only like 9.7K worth of data. So we're in roughly the right range, right? If we assume that the file has, some header overhead, it looked like it had resources appended to it for, well, it's not no particular reason. I think I think you actually have to give UPX an option to say whether or not you want to pack resources. So I think those resources right here are just like tacked on from the original hello world. Where's my original hello?
I take back my insertion.
Right. So there were definitely some resources on the original hello world. Let's see. But it looks like there's more on the packed version actually, so maybe not. But we can see that there's definitely like a bunch of resources and stuff there as well. So I would say we're roughly in the right range that it looks like there's about 6.8 worth of data there, and then we've got some extra header data. So as always, prove the assertion with proof pudding, and let's just like see what the code actually does. So from WinDebug, we're going to open the packed UPX that was in desktop code, Life of Binaries, debug, hello packed.exe. Right, so it's going to start it up. It's going to set a break before it starts executing anything. We're going to set a breakpoint at the base address plus 1CAF0. So for BP for breakpoint 0x4 1CAF0. And I'm going to drag that on here again. We got to get the same windows up again. Let's create a memory window, drag it to the top, and a disassembly window, drag it to the bottom corner. So your debugging environment should look like the above. You're going to have to like drag it, let it go, and then drag it back again. So like drag it till it's like hovering. Yeah, there you go. Now drag it back to the top. There you go. Yeah, sometimes it'll just won't do it unless you let it go somewhere else and drag it back to where you want it to be. All right. So we set a breakpoint at what we think will be the very first instruction of this unpacking code, right? So now let's go ahead and run it. G for go, and execute it. All right, so, oh no, we've got a instruction you don't know. Push AD is the D word form of push A, which is push all. So this is a thing which like dumps a bunch of registers onto the stack. It's like saying push EAX, EBX, ECX, EDX. So it's just pushing a bunch of registers on the stack, basically because eventually it's going to pop all those registers back off. So it's just trying to say like, let me save off all those registers and later on I'll restore them immediately before I jump to the original code. So if I were to take my memory window and put it to ESP, what I should see is that like a ton of registers get dumped onto the stack. Actually, let's get a registers window as well so we can see that. So 1, change your memory window to showing long hex D words. 2, this little thing that has an AX on it, that's the registers window. Click that, and let's split the memory window. Now we've got this four-way split. All right, so I'm asserting that basically all these registers are going to, well, most of the registers are going to get dumped onto the stack from this push A instruction. So go ahead and hit step into or step over just exactly once. So that steps over the push. And then go ahead and look at your stack. And so I can see, for instance, 119F554. That looks like my EDI. I can see 7BEB5A. That looks like my ESI. I can see 12FF0. That looks like my EBP, etc. So if you go to the Intel manual and you look up push A, because of course you can go to the Intel manual because you learned how to read the fun manual in the intro class. So go to the Intel manual and look up push A, and you will see the order which it pushes things onto the stack. Look up pop A, you'll see the order which it pops them off. Yes, question? All right, so those are all the registers that just got thrown onto the stack. And so it's going to do some whatever, and then eventually it's going to jump somewhere. So let's just step all the way through that and let it jump. And this is the point at which I say, and now it's up to you to read the code and figure out how to unpack it. No. So like I said, I didn't actually go through and even get a sense of what the Windows version of the code does. So I only did the Linux version. But basically, I'm going to see now if I can just eyeball and figure out where it's going to eventually call back to the original entry point. So, oh, there's an interesting thing. Immediately before there's a bunch of zeros, all of those add, byte, pointer, EX, those are all just the disassembler trying to interpret some zeros as instructions. Looks like there's a jump instruction immediately before it falls off the end of the world and starts looking at zeros. So I'm going to hypothesize that all of that assembly code before that is going to do a variety of decompression and putting the stuff into memory. And I'm going to hypothesize that this jump instruction eventually just says when everything is all said and done, just go ahead and jump to the original thing. Oh, and hey, look at that. There's a pop AD almost immediately before it as well. So if the very first instruction that this packer did was push all those registers onto the stack, it looks like there's this other instruction which pops all those registers off the stack pretty close to what looks like the end of the world. So I'm going to set a breakpoint on that jump instruction. And so I'm going to like literally just click on it. And then there's this little hand with the stop breakpoint instruction thing. So click on the hand. And then the jump will turn red. And so then you can just hit G for go. It will execute all the code up to that jump instruction. And now if I'm correct, where do we think this is going to go? All right, so if we think this is a jump to the original entry point, where is this going to go? You can use PEView to tell me where you think this is going to go. You must use PEView to tell me where you think this is going to go. In the original unpacked code, if this is jumping into the unpacked code, where is it going to go? I literally don't know, and I need someone to tell me. 111.
41110E.
41110E.
Yeah, that's what it says.
Oh, like that right there?
Yeah, kind of like that right there.
Kind of like that right there. So how did you find this address that you are hypothesizing that it's going to jump to?
The PEView looked at the address of entry point. Yeah,
right. So he went to the PEView for the unpacked one. He looked at the address of entry point, and he said, okay, well, if this thing just decompressed hello world into memory, it's probably just going to jump to the original entry point. So that was the original entry point, 41110E. It all worked out for me in the end, and it looked like I knew what I was talking about. So I'm going to step into this. And, oh my God, it's trying to trick me. All right, so do we think that's actually what the entry point of hello world looks like? Maybe. Let's open another debug window. You don't have to follow along for this because I want to see if that's actually what the original entry point of hello world looks like. It could, because that might have compiled it with linking, intermediate linking, whatever turned on. So breakpoint at that 4110E. Okay. So now I have a second window open. This has the actual unpacked version of it. I set a breakpoint at the original entry point of unpacked hello world. I get myself up disassembly, and I'm going to go. Yep, it is success. So it turns out that even in my original hello world, because I compiled it poorly, it has a jump instruction as the very first instruction that it executes. And that's what we saw here before I immediately jumped through it in order to get to the other code. So it's all good in the end. And we saw that. So now the point is, we can see where the packer starts. We can see where the packer ends. But your homework will be to understand what happens in the middle, right? So there's some code in the middle, which is going to, roughly speaking, right? So we now know, I mean, you maybe want to write this picture down or something, or just, go back in and look at PView for the packed version later. But we now know, roughly speaking, that the unpacker starts about here, and it's got some code down here. We think that the compressed version of the code is like in this memory above that, but we don't know that for sure. We need to go look at that code and see it execute and see if it like starts reading from here and like decompresses into here or something like that. So definitely, this is just the briefest of overviews of how packers work for a non-malicious packer. A malicious packer, in that in between the start and the end, there would have been, a bunch of stuff to screw with you, interrupts and exception handlers and things like that, obfuscated code so that it doesn't look the way you think it looks, jumping into the middle of instructions to get different instruction streams, etc. So that's a topic for the malware analysis class for when you deal with a obfuscated packer which is trying to hide what it's doing. Because the big point here is when the packer is eventually done, right, so we have the advantage here that we know what the original hello world looks like, right? We knew what that looked like. We could cheat. We could look at the P headers for that to know where this thing's eventually going to go. If this is malware that the malware author is trying to hide from you, you don't have this. You have this packed thing. This code is bouncing around in here, and maybe it eventually has a clear jump to here. Maybe it doesn't, right? And so your job, as when you're trying to unpack some maliciously packed file, is you need to figure out at what point the unpacker is done and the real code starts executing, right? You just want to analyze this packed file. And so you need to see when this thing is completely decompressed in memory, then you want to like dump it out of memory and go analyze that file, right? So when this thing is completely done decompressing, it'll have this hello world in memory. You want to dump that out to memory and go, look at that in PView, rather than this, packed, compressed version, right? Yes.
Yeah, but most people oftentimes, or most of, maybe in malware, not even have the PE headers and stuff.
No, there has to be the P headers for the original packed version, right? So if they're UPX
What
like
if it's
this,
just a routine though, right?
what if it's just a routine? So if you're talking about like some malicious like library or something like that, that's a completely different case, right? We're talking about, standalone executables. Most malware is going to be an actual, kind of exe. If it's something like, a shellcode routine, if you literally, just have shellcode, yeah, that doesn't stand alone, that doesn't have P headers. We're talking about if you recover some malware from an operating system, that malware has to have some way of running. It could be just a malicious library, which assumes that something else like run dll32.exe runs the library. But yes, there definitely can be cases where you don't have P headers for some malicious snippet of code, but far more commonly you're going to have, some obfuscated standalone binary which gets downloaded basically. All right. Any questions on the packing section? See if I have anything else to say about this.
And will it also depend on certain conditions, whether it unpacks or not?
Yes, actually. So right, the question is, will it depend on conditions whether it unpacks or not? And that's why I said a malicious packer is going to have things where they actually try to trick you and do things like that. If you're walking through the code, they'll try to trick you and see wrong things. But also, for instance, in the intermediate x86 class, we covered two particular examples where code can tell if it's being debugged, right? So the first one was it uses the RDTSC instruction, which is just a timestamp counter. It says, if the time when I access this timestamp, between that timestamp and that timestamp, if they're not within some range, then I think my code is executing too slow, probably because there's some human like stepping through my code. And they can say, if it looks like my code is executing too slow, then I'm going to go jump to some other code routine which does nothing, doesn't unpack, exits right away. Of course, if you just exit right away, then the human will understand something's up, they'll go back and look for it. So it's better if they send you on a wild goose chase. So that's one thing where they could say, based on the time it takes, that they're going to stop. Another thing is they could look for, like, if they have breakpoints in their code, right? So the other thing we saw in the intermediate class was, the breakpoint actually puts the hex CC byte into the code in line. That's why I just said don't have breakpoints in your virus when you copy it. And so that's another thing. They could be reading their own code and checking, like they could be just making a checksum of their own code. If that checksum doesn't match up, implying that someone has modified it, for instance, with a breakpoint, then the packer can just go off and send you on a wild goose chase, basically. So, yep, malicious packers are going to throw in all those sort of tricks to make it so that unless they think that that they're executing in a pristine, unmodified condition, then they won't execute at all, basically.
Say that again? What was the last comment?
What?
What was the last comment again?
I said a malicious packer can throw in conditions to its unpacking code such that unless the code thinks it's executing in a pristine condition, where pristine condition can mean its timing is what it itself expects of itself, its checksum of its own code is what it expects of itself. They can throw in those anti-VM checks we also learned about in the intermediate x86 class, where they can check, does it look like I'm in a VM? If so, I'm not going to run, stuff like that. Any further questions about packing? So in your slides, you'll find that I pointed out the difference between, my particular version of Hello that I happen to have at the time. It's not the one that I just showed here. It looks like that one is a release build rather than debug build. But, I just pointed out specifically the places where stuff is going to differ between these two versions. And then also there's the alpha version, which unfortunately we definitely are not going to have time for. So it looks like, Alf's going to get the can on this class as well, but we're going to get through the rest of this miscellaneous interesting stuff about few here, I guess. And this is the pseudocode, which is roughly applicable to, so this will be roughly, you can use this pseudocode, roughly speaking, to analyze the Windows version or the Linux version, I believe, because I believe with the Windows version, if we had dug into it, we would see that it starts at the entry point. Eventually, it's going to may not actually mmap a page because it has all of the memory that it already needs. So pretend it doesn't mmap the page, and it doesn't copy its own code because its code. So the key point here is this unpacker code is actually executing in memory space below the original space of this thing. So when it unpacks this entire original hello world, it unpacks from 0 to 1B. 0 to 1B, and that means this code down here, it's not going to get overwritten. In the Linux version, actually, it's slightly overlapped, so that some of the stuff gets overwritten, but not all of it. So it actually allocates some extra space for itself. So anyways, never mind. Don't use this for analyzing the UPX one. There's probably a bazillion things out there that can tell you how to unpack UPX, like unpacking tutorials and stuff like that. But you can just kind of step over all the instructions, step into some calls if necessary, stuff like that. Right, so the only other kind of miscellaneous things I want to say about packers is, one, like I said already, malicious ones are going to be introducing a bunch of anti-debug tricks, which is basically trying to either, make sure that they only run in, non-virtualized environments, make sure that they only run when there's not a debugger attached to them, etc. There's another type of packer which actually has a completely different form from this packer. So in this packer, the whole point is it just compresses down code and decompresses it at runtime. A different type of packer actually takes the x86 code from, say, hello world.exe. It takes the x86 code and it translates that code into a completely different, quote, language. It changes it into sort of like one of those intermediate representations that we saw in the very beginning of class, or a better way of saying it is it's more like it turns it into a form of bytecode, sort of like Java. So, you know, you may have heard of the Java VM, right? And you know that a Java VM is not like a VMware sort of VM, right? So there's what's called software virtual machines. That's like a Java VM, where it's a virtual machine executing virtual instructions, which eventually get translated into real instructions for a machine architecture like x86. And so what these packers like MITA or VM Protect do is they take x86 codes, and if you have, you know, an x86 instruction that says add, you know, 4 to EAX or something like that, these have their own virtual machine with their own virtual registers, and they turn that into add 4 to virtual register 1, something like that. And then if you have, you know, a, let's say, jump to some absolute virtual address, what their virtual instruction will be is like, you know, jump to some completely different virtual address within their virtual execution space. So I feel like I'm not explaining this clearly. For a second here. I guess the point I want to make about these software virtual machine kind of things is that just like a Java virtual machine, which takes some stream of bytecode. So a Java virtual machine takes what's called bytecode, and those are sort of like fake assembly instructions. They're fake instructions that say to do some operation. Eventually, those instructions are translated down to doing some operation on the actual x86 machine. Right? They change real registers eventually. Similarly, these software virtual machine style packers will take whatever x86 code you happen to have in your hello world. So let's say in hello world you also had a subroutine, you know, function 1, and the function 1 did some sort of calculation like variable 1 times 3 plus 4, something like that. This notion of variable 1 times 3 plus 4, you can implement that directly in, you know, x86 assembly language, and you put, you know, variable 1 is EBP minus whatever, and you have some data value there, and you take that and you multiply it by 3, and then you add 4. But you can just as easily do this on virtual registers, and you can say my virtual register gets loaded up with my virtual local variable, and then I'm going to take that virtual register and multiply it by 3, then I'm going to add 4. So when you're analyzing something which is packed with a MITA VM protected sort of packer, you will see x86 instructions executing. But those are not the true x86 instructions which were programmed up by the original programmer. The original programmer wrote their little C hello world, and they said, okay, let's run this through the MITA now. The MITA is then going to potentially take, you know, some set of functions from that executable. It's going to translate them into a new language, and it's going to have an interpreter for that language. That's the actual virtual machine. And it's going to say, I'm going to turn this function into this sequence of virtual instructions, and I'm going to have a virtual instruction interpreter brought along with it. So it basically is, you know, a huge expansion in the size of the code, but it's a huge obfuscation in terms of you understanding what's going on. So when you read actual x86 code, you can have a rough sense of, okay, it looks like they pushed some values and then they called a function, right? You have a sense of that. But when a single push instruction in the original x86 gets turned into, like, you know, however many x86 instructions correspond to one virtual push, that's when it gets really hard to figure out what the original code was trying to do. Because there's this massive expansion from compact, quick x86 machine instructions to big fat virtual instructions which have some underlying, you know, many complicated physical instructions. So it definitely makes it harder to analyze what's going on, what the original malware is trying to do. So just wanted to point that out so that you know that if you ever have to deal with that, it's going to be a huge pain in the ass. All right. And then just a miscellaneous thing here. This was the most recent one I could find, and I don't think it's that recent since it's DEFCON 15. It's like 2007. But the funny thing that you see when you go find things that talk about Packer distribution is that, like I said, UPX is like the simplest thing to understand, and yet it's still used in a lot of malware due to whatever reason, laziness, they don't care, ignorance. This is a little problematic here in that these two things were misidentified, I believe, as just trying to say that. Well, I think this is just misidentifying what the actual, quote, packer was, and that it's not necessarily actually packed. Then there'll be just, a bunch of other packers. So there's pcompact, there's ASPack, FSGPpack. So there's like all these different things. And if you go back and you go to that slide, you'll see this is actually just for the packers which have 100 files or more. And they had some malware collection, and they threw it through a packer identifier, probably PID. And then they said, for all of our malware collection, we have 3,000 files that are identified as being packed with UPX. We have 988 or 762 which are identified as ASPack, whatever. And so there's many files like that, but then eventually you get into all this long tail here that there's a bunch of miscellaneous small little packers that aren't used by very many people. They're like only used potentially by some groups. And they have this long distribution of everyone has their own little custom packer. So whereas you may understand the general notion of how UPX works, therefore you can just skip ahead to like, oh look, there's a jump instruction. I think I'll go to the last jump instruction, right? When you start dealing with the fact that there's like hundreds or maybe even thousands of different types of packers out there, you can no longer, use simple, quick mental notes. You start having to deal with each of these every time you get a new packer and you say, is this something I've ever seen before? And when you become, an experienced malware analyst, you're going to have seen a lot of these, right? You'll see probably all of the top ones, and therefore you'll be able to have mental shortcuts and or helper programs to help you get through the top packers. But it's all of this this lower order tail that there still can be like lots and lots of stuff that you've never seen before potentially, or which are just variants. Frequently, the point is the reason why there's all these like many different variants at the end is that they're variants specifically to try to break tools which are meant to auto-unpack them, right? So ideally, you just want tools which auto-unpack and spit out, the original hello world.exe. But as the packers get better, they make it so that, they're going to be potentially polymorphic, actually, so that they, for instance, this code over here, right, in UPX, this code, which does the unpacking, is the same every time, right? This code can start being polymorphic, and they can start doing different instructions for this, and that'll make, the overall thing will be significantly different. And I guess I probably should have said this as well. With respect to, you always see these stupid discussions of things where they talk about zero-day malware, which I don't like the term zero-day malware because there's zero-day exploits, which is an exploit which you've never seen before. Zero-day malware theoretically then is malware you've never seen before in the sense that you've never seen its hash or it doesn't have this antivirus signature. I don't like that term. It's really just a new malware variant that you haven't seen before as defined by something like an MD5 hash. Now we said that if this is all the compressed data right here and this is the unpacker itself, this is the actual stuff which is on disk. Right? So we said there was like some amount of this right here which was on disk and mapped into memory. This compressed stuff can also be encrypted, like I said before. And if we encrypt this, then we know that anytime we choose just some random key, then this data is going to be changing. And therefore, I can pack hello world twice, the exact same hello world, and, with two different encryption keys. And because of that, this encrypted stuff is going to be completely different. So the hash of the entire file will be different. So, I've never seen this file before because the hash doesn't look the same, right? So the notion of zero-day malware and the fact that you haven't seen it before is not a particularly good notion. And so some of the packers, specifically the point is, to encrypt this to make it look just like it's new, and then to polymorph the decompressor so that it looks like something you haven't seen before, right? Because otherwise, if this is always the same, antivirus will just set a signature on the decompressor code, and it'll always match. So then they start making that vary so that you can't just set a signature on that. Anyways, did I give you guys a 4 o'clock break yet? I don't think so. All right, 5-minute break. OS loader, the things that do things like load library and stuff like that. Okay, I don't think that's correct, but it hooks some of the functions and DLLs in order to actually, in order to trick it into thinking this version which the attacker has injected into memory is a version which was loaded up by something like load library, basically. So this is a fully self-sufficient version. Otherwise, if you're trying to inject a DLL into an exploited process, you need to play with the functions to trick them. That's why there's a blank thing. I was going to put in a picture, and it needs to be animated and stuff like that to make sense. But, all right, hot patching. I feel no passion for speaking about hot patching because this was demanded by my wife because she says that this is part of the life of binaries. What can one say about hot patching? Boring. Okay. So, Microsoft would like to have the ability to update things on the fly. So the hot patching refers to the fact that we want to patch an executable while it's running, right? We don't want to like shut down, restart the system. We want to take some component which otherwise would require a restart and allow us to change it in memory in such a way that it'll still run as normal, but we didn't require shutdown, unload, or anything like that. There's a hot patch linker option, or sorry, compiler option, which you can specify. And this is actually where in some functions, if you see that the function starts with this move EDI to EDI instruction, the only reason that's there, it's a no-op, obviously. If you move a register to itself, it doesn't do anything. The only reason that's there is because the normal 2 first instructions are push EBP, move ESP to EBP. Those 2 instructions are 3 bytes. That's 1 byte, that's 2 bytes. If you put this in front of them, that's also 2 bytes. Now, this plus that equals 5 bytes. 5 bytes happens to be the size of 1 byte jump opcode, and then 4 bytes address where you want to jump. So, by making it so that the first instructions, the first 3 instructions of your function are move EDI, EDI, push EBP, move ESP, EBP. By making those the first 5 instructions, you can guarantee that as long as you overwrite the first 5 instructions of a function with a jump, you know what instructions you need to replace eventually before you go back to wherever you overwrote functions. So, that's the whole point of hot patching. Done. You can see a bit more here where he talks about all the different ways that one can do hot patching. The thing I just talked about was just the simple case where, you know, if Microsoft comes along and let's say there's like a DLL which has a buffer overflow in it. Microsoft wants to come along and they say, I want to fix this on some servers, but I don't want to have to force people to reboot the servers. So what they're going to do is they're going to come along with a patch which says, okay, for my vulnerable DLL, I'm going to insert a jump instruction at the beginning of that DLL. I'm going to inject a DLL into the memory space of the vulnerable thing, insert a jump instruction. The jump is going to go off and have, you know, some completely different implementation, you know, some slightly modified implementation of the function which is no longer vulnerable to the buffer overflow. And when that thing is done, eventually it will, oh, see, even that's still not right. I tried to fix this up to make this correct. I was feeling very lazy and I didn't want to just write my own thing that had, you know, a couple of instructions. But I did not still fix it up correctly because there should be a move EDI to EDI right here. So the point is, for those 5 bytes worth of instructions that you overwrite with a jump at the beginning of a function, you need to create a copy of those somewhere so that before you jump back to the original, you do move EDI to EDI, push EBP, move, well, I guess theoretically you don't need to do the move EDI to EDI, but for simplicity, you would just take those exact 5 bytes and you put those exact 5 bytes at the end of your thing, right? So you do those 3 instructions and then you jump back to the address immediately after the original thing and it would do whatever it's going to do. So that's actually just a plain jump overwrite. You know, that's used by rootkits in order to man-in-the-middle stuff as well. We'll go into this a bunch in the rootkits class as well. You just change the instructions. This is actually what that import address table hooking from that DLL that actually hid the calc.exe. The original version did this rather than hooking the import address table. Do you have a question?
Yeah, I'm kind of How would you do that on a running system where the processes do it? They have to lock it somehow.
Yes, they would certainly have to like lock it down and like say, stop, don't call this function, right? And then don't call this function. Make sure it's not in the function right now. You'd have to say for all the running threads, are any of them in the middle of the thing, right? So it's certainly complex, and there's a lot of stuff you have to actually check to make sure no one is currently executing something before you redirect control flow, right? But if you, check everything to make sure no one's currently in the middle of stuff, then you can, not schedule any other threads to run right now so that you're the only one who's running, and then go ahead and go in and change the stuff.
Seems like that would probably introduce new bugs to the original bug.
Potentially, right? So we asked, would that add more bugs? Potentially, but, Microsoft's got it down at this point, so I'm sure it's all bug-free. So that was hot patching. Now, I think, this is going to be the last thing I'm going to cover. No, there's two things I'm going to cover still. This one is basically just a funny little thing that you can see of, now that we know some things about the PE format, there's actually some people who play hackery with like PE format or the ELF format, etc. And so they asked the question, what's the smallest possible executable that I can still run on Windows? So if we go to freedom.org, we'll see that they found an executable. Now this isn't like an executable that does like printf or anything like that. This is just an executable which returns 42, I believe. So if you go to this, page, it's going to say, okay, I have a simple executable which just returns 42, and I compile that, and then, oh no, it looks like that simple executable is 45K. Right? And so then they just keep digging down, and they say, okay, well, what can I do to make it smaller? All right, now it's only 1,000 bytes. Now it's only 468. And so if you walk through this little tutorial here, you'll see that they start doing things like hacking data into the MZ header. They're saying, like, I can reuse all of this unused data in the MZ header because I only care about the magic, and I only care about the ELFA new. So I can start using that data for whatever I feel like. And so basically they start identifying all the what they consider useless fields in the thing, and they're saying, I can put some data in there, I can put code in there, and I can start having an executable that's tiny. Right, so again, that's a on your own time kind of thing, but now that you've actually seen some of these, you can sort of understand. You'll see that most of the things they say are useless are the things I say are useless. Yeah, they got rid of the data directory entirely, right? So there is no data directory for this executable. And so eventually, la-di-da-di-da, there's a lot of explanation, so they're very thorough in explaining it. But this is just sort of a, if you're interested in games nerds play, go check those out to see how they hacked their way through in order to make tiny executables. All right, this is sort of a practical tool just to take a look at. You're going to want to take a look at these slides. And this binject tool, I believe, yeah, it was released this last summer. And this can do some interesting things like sticking TLS callbacks into functions, into executables and stuff like that.
I was going to ask a question. Is there any limit to what you can do in the TLS callback?
Define limit.
Like, I mean, could you do your entire execution
Yes.
in TLS? Okay.
Right, so his question was, is there any limit to what you can do in a TLS callback? Can you do the entire executable in a TLS callback? Yes, you can. Because the point is, right, it's just pointing, the TLS callback is just pointing at some function which should execute, right? And so if you zeroed out the address of entry point and you stuck the address of entry point as that TLS callback thing, you'd be functionally equivalent, right? So, there we go. He uses PEview as well.
Uses what?
PEview, right? So this is actually out of PEview, right? You can see this is our thing. So here's an example where he actually takes and he runs binject over an executable, and he's, quote, poisoning the import address table. And so these were those import address table descriptors, right? So we have one descriptor for each of the modules which we import. So he could say, okay, well, I want to make a Trojan version of this or that executable, say Notepad. I want my Trojan Notepad to always load up the evil.dll. And so for all of those versions that you want a Trojan, you don't have to use something like DLL injection. If no one's going to notice the fact that you have overwritten the original notepad with the Trojan version, then you can just make modifications like this to make sure that it's always Trojan. So, and then here's an example of, he's got the option in here in order to inject a TLS callback. And there's a bunch of other stuff. So I'll let you check out that as well.
Where was that link?
This was Binject on,
Okay, I got it.
on the Binject slide. All right, and now that we are sufficiently pared down to only the awesome people.
Only the what?
Only the awesome people, right? Now we're just going to tear down here. So we'll talk about the summary of what we learned in here, right? You know what you learned and you know what you didn't learn. That's okay. So the basics of what we talked about, right? Compilation, we talked a lot about, well, we didn't talk a lot about lexical analysis. Lexical analysis, right, was just how you specify the different tokens for your input things. So you have some C source code file and you say that my different lexemes are specified by a certain regular expression, and this is how I can group them into tokens. Syntax analysis, we spent a lot of time on that. Those are the context-free grammars, parse trees, which were the concrete syntax trees. And then we had the ASTs, the abstract syntax trees, where the only difference between a concrete one and an abstract one is that the operators were the internal nodes, right? Those ASTs were much smaller than the full parse trees. We had the AATs, the abstract assembly trees, which were how we eventually, using those AATs, we could like spit out directly, you know, for this tree, I'm always going to spit out this actual x86 assembly code. And the reason I think that's definitely useful to know about is when you see the simple unoptimized assembly code, right? So if you go and write, so I think in the intro x86 class, there was like one example, I think it was example 6 or 8 or something like that, where there was an if statement and we said, there was an if statement and when we looked at the assembly for it, there were 2 jump instructions and one of which you could clearly never actually get to. So when you start thinking about the fact that the compiler is maybe just like spitting out pre-computed things, like if I see an if statement, I do if and then, or I do like a compare and a jump, and then if I have an else statement, I do this. When you recognize the fact that a compiler can potentially be like spitting out just some fixed assembly instructions, you can start seeing how it could potentially make sort of weird-looking simple assembly. Linking, unfortunately, we have not yet found a good way to talk about other than to repeatedly say it splices it all together and to put our fingers together like so. So most of our time was obviously spent on the PE format, where we learned a heck of a lot of stuff about it. 3 flavors of imports. We have regular imports, bound imports, and delayed imports, right? And the delayed imports is just at some point later, it's going to import this DLL just in time. We saw MS Paint only imported UX theme when eventually someone called one of its delayed functions. And we saw hooking the import address table in order to hide things from Task Manager. Right? Hide calc.exe. Saw a bunch about the exports and how the OS loader goes and reads the exports from one module to fill in the imports of another module. And theoretically, we would have seen about hooking that. We didn't see that. We just talked through that. We also saw export forwarding, which was that way that kernel32.dll could redirect, its what was it called? Add vectored exception handler or something like that. Kernel32 redirected to ntdll.dll. So that would actually implement the thing. And we said the export forwarding was relevant because, Stuxnet had export forwarded the majority of the things for the module that it actually wanted to Trojan, and it implemented the version. It implemented Trojan versions of functions it did care about, and it forwarded else everything it didn't care about. We saw the relocations. We said the whole point of relocations is just that if a module gets moved in memory, there's potentially a bunch of addresses within it that have hard-coded, there's a bunch of instructions potentially in it that have hard-coded addresses, and those hard-coded addresses need to get moved if the base address is not correct anymore. For local storage, the only reason we care about that is because of those TLS callbacks. If you don't know that there's such thing as TLS callback, malware that does know that there's such thing will be able to execute their code and you won't see it executing. Resources, we said, is just sort of like a pseudo file system where you can have a bunch of data and things like that. And we said the interesting thing there is for executables like Process Explorer, which embed entire executables into their resource section, and Gmer actually does that as well. So the Process Explorer, it had a full kernel module that it drops out and then loads up just in time. And again, Stuxnet had like a bunch of resources for each of the different DLLs and kernel modules and stuff like that that it wanted, shellcode as well. And then we saw digital signatures, and I think that was the last one. We also saw some things, miscellaneous things. That load segment about a load config thing had the information about the stack cookies and then the safe structured exception handlers. And we saw nothing about ELF. I'm sure everyone's really unhappy about that. And then we saw how viruses work. We saw how one particular virus works, right? There are many possible combinations of how one can implement it, and you can now have at least enough knowledge to go out and look up how different implementations work. So we saw the simplest possible example of packing with UPX, where it has very simple code that just starts out, decompresses the code, and eventually just jumps to the original code when it's decompressed in memory. And so again, we saw there was definitely the compression of size of the executable, and there was the making sure that even though the size on disk was compressed, the virtual size still needed to be as big as the original executable, right? Because otherwise, the original executable could not be completely decompressed in memory. And I didn't really talk about DLL injection that much for the smallest binaries, etc. So with that, do we have any questions on the phone or questions from anyone in here on any of the stuff we went over? All right. I will let you go then.